Hello, today we'll look at some geometry essentials from Appendix A-2. So the content of this appendix is primarily it's the Pythagorean Theorem and some formulas for areas and volumes and so forth, perimeter for various geometric objects. We'll also at the end look at similar and congruent triangles. So to get things going on the Pythagorean theorem part, we need to talk about right triangles. So we'll define a right triangle to be a triangle that contains a right angle, that is a 90-degree angle. The side of the triangle opposite the 90-degree angle is called the hypotenuse, and the remaining two sides are called the legs of the right triangle. In Euclidean geometry, and what makes Euclidean geometry Euclidean is the parallel postulate, the Pythagorean theorem holds. It doesn't hold in non-Euclidean geometries, though. In fact, the Pythagorean theorem is equivalent to the parallel postulate with the appropriate other axioms laid out. Not our problem so much, but I've got some notes posted online. These things in red in all these notes I have are actually hyperlinks. So if you'll click on that, that'll take you to some notes I have on Euclidean geometry. Some notes on non-Euclidean geometry are available as well to show what happens when we deny the parallel postulate and what alternatives that leads to. But everything's Euclidean for us. And the Pythagorean theorem holds, which will state as follows. Certainly not bother to prove it, though if we did some axiomatic geometry, it'd be one of the big results. The Pythagorean theorem says in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So if we give the hypotenuse length C and the two legs lengths A and B, then we get the formula a squared plus b squared equals c squared. The Pythagorean theorem doesn't simply say a squared plus b squared equals c squared. A, b, and c have meaning. And of course, the most important thing is the Pythagorean theorem only applies to right triangles. In fact, the converse of the Pythagorean theorem also holds. I'll state that as a kind of a separate result. Says in a triangle, if the square of the length of one of the sides equals the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. So this allows you to conclude triangle is a right triangle, provided a squared plus b squared equals c squared for some choice of a, b, and c in the given triangle. So the Pythagorean theorem is it's called an if and only if result. A triangle is a right triangle if and only if the square of one of the sides equals the sum of the squares of the other two sides in length. And of course, the 90-degree angle is opposite the longest side. We could now introduce the term for the longest side as the hypotenuse if we know we have a right triangle, and there you go. So let's illustrate some applications of the Pythagorean theorem in terms of geometry that will apply. Probably the Pythagorean theorem is the most common thing from geometry that will apply in Precalculus 1. It will play a big role in Precalculus 2 as well when you start looking at trigonometry. So some examples in the supplement containing examples and exercises. Let's look at number 14 from this appendix. If the lengths of the legs of a right triangle are a equals 6, b equals 8, and c is the length of the hypotenuse, then find c. Okay, so it's very much set up in an a squared plus b squared equals c squared style because they've given us the stuff we need, right triangle, and the lengths of two sides, so labeled. Pythagorean theorem tells us we have, with this assignment of a, b, and c, a squared plus b squared equals c squared. So C must satisfy. A equals 6, so we'll get 6 squared. B equals 8 plus B squared plus 8 squared. 6 squared is 36. 8 squared is 64. Sum those, get 100. We must have C squared equals 100. Let's do this very carefully. What numbers when squared equals 100? Well, there's two of them. So C is either -10 or +10. But, of course, -10 can't be the answer because C is a length and lengths are never negative. Since C is a length, it can't be the -10, so it must be the +10. And we draw the conclusion that the hypotenuse of this right triangle must be 10. Pythagorean theorem. Let's tweak that idea a little bit. And suppose you're given 3 lengths. The lengths of the sides of a triangle are 4, 5, and 7. Determine if the triangle is a right triangle. If it is, identify the hypotenuse. So we need to check and see if one of these squared equals the sum of the squares of the other two sides. The converse of the Pythagorean theorem tells us if that occurs, then we have a right triangle. The Pythagorean theorem itself tells us if that does not occur, then we do not have a right triangle, which will be the case here. So we need to square 4, 5, and 7. 4 squared, 16. 5 squared, 25. 7 squared, 49. And let's see if one is the sum of the other two, and it isn't. 16 is not the sum of 25 and 49 because 25 plus 49 is too busy being 74 to be 16. 25 is not 16 plus 49 because that's 65. And 49 is not 16 plus 25. It's close, it's 41, but not equal. Of course, it would have to be that the longest one is the sum of the other two in the squaring sense. Really, if I think in that sense, I've only got to check this last one. The first two couldn't possibly hold. But we'll just check all 3 of them since we got the numbers in front of us. So the converse of the Pythagorean theorem, strictly speaking, doesn't apply. Had any one of these been an equality, we would have said right triangle. Technically, we got to go back to the statement of the Pythagorean theorem itself. It says if we have a right triangle, then the square of the length of the hypotenuse is equal to the sum of the squares of the other two sides. This can't possibly hold. So that's the reason that we can draw the conclusion that these are not the lengths of the sides of a right triangle. Strictly speaking, it's the contrapositive of Pythagorean theorem that we've used, not the converse. The converse failed to apply. It's the contrapositive, something logically equivalent to the Pythagorean theorem that tells us if we do not have an equality in any of these, then we do not have a right triangle, and we do not have a right triangle from those lengths. All right, let's look at something a little more exotic. All we have at our disposal at this stage is the Pythagorean theorem for this appendix. The following story will draw a picture. This book seems to like mixing units together. Here they're going to mix feet and miles. So we'll have to deal with that. The story is a person who is 6 feet tall is standing on the beach in Fort Lauderdale, Florida, and looks out into the Atlantic Ocean. Suddenly, a ship appears on the horizon. How far is the ship from the shore? So, person is 6 feet tall. Horizon, Earth. We'll treat the Earth as a sphere. And we'll have to introduce a right triangle because this stuff is all about the Pythagorean theorem. They give us the radius of the Earth, which is an important parameter, but they give it to us in miles. And we're given distance measured in feet up here when we talk about the person. So we'll have to get common units, maybe express the radius of the Earth in terms of feet. Let's do that. That's the way I've typeset it anyhow. You could equally well express the height of the person in miles if you want, but 6 feet is not a very big piece of a mile. Let's do it in terms of feet. Okay, so we'll treat the Earth as a sphere and take a cross section of it. So here's the picture we've got. Don't worry just yet where these numbers came from. We'll compute those on the next slide. But we're going to take the center of the Earth to the horizon. So here's where the ship is. That'd be the radius of the Earth, would be this distance here. We'll see that in terms of feet, that turns out to be 20,908,800 feet. So here's the distance from the center of the Earth to the ship sitting on the surface of the Earth. And the person 6 feet tall. So how far are the eyeballs? Actually, we're treating the eyeballs as if they were on the top of the person's head. That's sort of implied in the problem. So that's the way it's intended to be worked. We could certainly argue over that. We'll take that distance from the center of the Earth to the surface of the Earth and add 6 feet to it. Certainly this ain't to scale. So whereas we had 20 million, blah, 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 800 feet, here we'll get 20 million, blah, 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 806 feet. That 6 right there corresponds to the height of the person. So we've got the ship treated as a point setting on the horizon, and we've got the person looking 6 feet above the horizon. And we could modify this, easily to change the numbers and say if a person stands on the top of a 3,000-foot mountain, how far can they see? Just by changing the 6 feet to say 3,000 feet. And we'll do the same type of manipulations we're about to do. But there's the right triangle. We've got a tangent. Here the person's looking to the horizon, so that generates a line tangent to the circle. Tangent lines to a circle are at right angles to radii of that circle. So that's the reason we get a right angle here. We got a right triangle. There's the hypotenuse. There's one of the legs. And this distance D is labeled in the picture. That's the other leg. And that's the distance we're looking for. So there's the plan, a plan that uses the Pythagorean theorem. We need to see where these numbers come from. This is the radius of the Earth. We were told the radius of the Earth is 3,960 miles, and that 1 mile equals 5,280 feet. So the radius of the Earth in feet is 3,960 miles times the conversion factor, 5,280 feet per mile. Notice the units of miles cancel, and we'll be left with units of feet. 3,960 times 5,280 feet. Not big on calculators, but this is certainly the time for a calculator to do this arithmetic. Multiply those together, and that's where the 20,908,800 feet came from. So this is what we had for the radius of the Earth in the picture on the previous slide. The observer is 6 feet tall. So we'll say the observer's eyes are 6 feet off the ground. That's the top of the observer's head and not exactly where his eyes are, but let's make that reasonable approximation. And so we'll get 20,908,806. So there's the height of the observer. And this gives us the picture we saw on the previous slide. We made the comment, lines tangent to a circle are perpendicular to the radius of the circle, and that's what gave us the right triangle. So we're interested in, let's look at the picture one more time. Hypotenuse squared equals unknown squared plus this distance squared. So we'll have the relationship this squared plus that squared equals hypotenuse squared, and that'll give us a relationship in which we can solve for D. Right triangle. So we've got a right triangle. The Pythagorean theorem tells us radius of the Earth in feet squared plus a distance one can see. That will come out in feet as well because we've chosen to do this in feet. We'll convert it to miles just to make more sense out of it at the end. But we get one leg squared plus the other leg squared equals the hypotenuse squared. The hypotenuse is a long one, and it ain't much longer than the others, but it's 6 feet longer than this one. That produces this equation. We'll rearrange it, solve for D squared, take this to the right-hand side, it becomes negative. We need to crunch these numbers, and you'll see that we get 205,000 205,905,636 feet. Actually, my units are off. This would be feet squared because it's d squared. I got the units correct there. This should read feet squared. Little typo. I'll fix all, well, hopefully not many, but I'll fix a few little typos that I find and update the notes. So here's d squared. We'll take a square root of that. That'll give us units of feet. Taking a square to 205 million and whatever gives us 15,840 feet. That's how far the person can see on a perfect sphere who's 6 feet tall. Let's take that and convert it to miles to make a little bit more sense. It turns out it's precisely 3 miles. If you'll divide 15,840 feet by 5,280 feet, then you will get 3 miles. So use a conversion factor again, that'll produce 3 miles. And that ship must be then 3 miles away from the observer. Actually, technically from the observer's eyes is how far the ship is away. So there's an example applied to circles of the use of the Pythagorean theorem. In it all, it's based on the fact that a tangent to a circle intersects a radius of a circle at a right angle. So you got to have that right angle stuff if you're going to use the Pythagorean theorem. Back to the notes and somewhat different topic. Let's look at these figures and make that a little bit bigger. I'm trying to get it all on these slides. We're considering a rectangle of length L and width W, as the parameters are labeled in this picture, a triangle of base B and height H, a circle of radius R and diameter D, a box of length L, width W, and height H, a sphere of radius R. They've shaded it to try to give a concept of depth to it, so it's a sphere, and a cylinder of radius R and height H. We want to find areas and, when appropriate, in the last 3 volumes. For the rectangle of length L and width W, the area is L times W. The perimeter, the distance around that rectangle, is 2L plus 2W. Yeah, we go L plus W plus L plus W to find the perimeter. And sure enough, that's 2 L's and 2 W's. The triangle with base B and height H, base B and height H has an area of 1/2 B times H. By the way, in practice, somebody gives you a triangle, probably easy enough to find the base. Depending on the information you're given, finding the height might be a little bit more tricky. If you're simply given the height, you're good to go. If you're given a right triangle, turns out it's pretty easy to deal with. If you're not given a right triangle, finding the height is likely to be the most complicated thing. It depends the information they give you. But given base and height, the area of the triangle is 1/2 base times height. Circle of radius R, or equivalently diameter D equals 2R. The area of a circle is pi r squared, and the circumference of a circle is 2 pi r. Well, 2 times r equals d, so we could also write that as pi times d. All right, let me make it a little bit smaller here so we can see the pictures and the formulas at the same time. For the closed rectangular box, what this means is it's not an open box. It's got a top and a bottom and a total of 6 sides in all. But that's what they mean when they say closed rectangular box of length L, width W, and height H. The volume equals length times width times height. These formulas don't explicitly keep up with units, but you might notice when I multiply 2 distances together, then we get units like square feet or square inches. It's an area. It should be square feet or square inches or square centimeters. Down here, we're talking volume for the first time. We've multiplied 3 distances together. All right, that'd give us cubic feet or cubic inches or cubic centimeters, cc's. So volume is simply, for a rectangular box, the product of its three dimensions. The surface area, it says, is 2LH plus 2WH plus 2LW. This could become a lot of stuff to remember, but look at the box. The front of this box is a rectangle. Dimensions are L and H. So that's where the LH came from. That's the front of the box. Where did 2 come from? Well, the back of the box has the same dimensions. WH, here's W and here's H. This is the, from our perspective, the right-hand side of the box. We get 2 of those, the other one for the left-hand side of the box. That just leaves the top and the bottom. Notice the bottom is L by W, so we get 2LW because those are the dimensions of the top as well. Hey, we got 2 times something plus 2 times something plus 2 times something. There's 6 things here. Yeah, they're the areas of the rectangles of the 6 sides of the box. So think like that, and there's less stuff to remember. For a sphere of radius r, the volume is V equals 4/3 pi r cubed. The surface area is S equals 4 pi r squared. In practice, if you need these on a test, for example, I'd probably state these for you. These are not particularly intuitive, but I'm hoping you know the area of a circle is pi r squared. But the volume and the surface areas of a sphere, it's not intuitive. These ideas date from, I think it's Archimedes that first does this. It's involved to find the volume and express it in terms of the radius and the pi's and some constant. In calculus, you'll have ways to do it. Guess what? 2,500 years ago, Archimedes had some very deep ideas along the lines of calculus. And that's the reason these formulas are tied to Archimedes. But you'll elaborate on where these come from more in calculus. We'll take them as given, and in practice, if you were to need them on a test, I'd probably state, especially these kind of things here that I view as a bit more exotic, I'd state these for you. The closed right circular cylinder, let's look back at the picture of that. It's basically, it's can. Closed means it has a top and it has a bottom and it has the sides. Height h, radius r, the claim is the volume is pi r squared h, and the surface area is 2 pi r squared plus 2 pi r h. And these dimensions, or these volumes and surface area, should make sense. We've got a surface area on the top of pi r squared because it's a circle on the top. And we've moved that through a distance h to produce the can. It makes sense. This area times this distance would be the volume. That'd be pi r squared times h for the volume of the cylinder. The surface area, that'd be the area of the top plus the area of the bottom plus the area of the sides or side. We said it was 2 pi r squared. Oh, there's pi r squared twice. That's the top and the bottom. 2 pi r h, 2 pi r, sounds familiar. That's the, here it is, that's the circumference of a circle. So we've got the circumference of the circle here, and then it's multiplied by dimension h. Where that comes from is, if you'd think of this cylinder, maybe made out of paper, remove the top and the bottom, then you've just got like a paper towel roll. Cut it open and peel it apart. Then it'd be a rectangle. Its height would be h, and its dimensions from side to side, width, would be the circumference of the circle. So one dimension would be 2 pi r, and the other one would be h, and that's where this expression comes from, the area of the wall of the cylinder. So let's use those in a couple of examples. Here's a picture, straight from the book. Find the shaded area. Okay, let's use those formula we just introduced. Let's treat this as a square, 2 by 2 square. Length L, width 2, L equals 2, W equals 2. To match it up with the symbols introduced in that previous note. And then the area is 2 times 2. The area is 4 square units. They didn't tell us what the units are, so I don't have to worry about them. but it would be square inches or square feet. It's an area, so square somethings. So we get an area of the square of 4, but the shaded area has removed this circular part inside. That circle, which will be removed, has a diameter of 2. Side to side, top to bottom is 2. So the radius is half of that, and the radius is 1. So the area of that circle, let's denote it as A sub c, would be pi r squared, where r is 1, would simply be pi. So the area of the square is 4. The total area of the square, right, includes the stuff inside the circle as well. That'd be 4, but we've removed pi from that. So the shaded area, in terms of the symbols I introduced, would be area of the square minus area of the circle would be 4 minus pi. And that's the area of the blue region. Finding areas of things with curvy sides, that can be hard. It's one of the things you'll do in Calculus 1. We're given a formula for the area of the circle, pi r squared. It's contained in Euclid's Elements, by the way, tying it in a lot more with geometry. But in general, if this was a more exotic curvy shape, we probably wouldn't know how to find the area with the equipment that we have now. A similar example, word problem of sorts, says a circular swimming pool that's 20 feet in diameter is enclosed by a wooden deck that's 3 feet wide. What's the area of the deck, first off, and how much fence is required to enclose the deck? Okay, diameter of the round pool, 20 feet, got 3 feet of decking, and then we got 3 feet on this side and 3 feet on that side. I want to think in terms of diameters and radii of circles. Diameter of the pool, d sub p, is 20 feet. Most of our formulas involve radii. So let's look at the radius of the pool. Let's call it r sub p, p for pool. Radius of the pool then is 10 feet, to keep up with those units if they give them to you. The diameter of the circle determined by the outer fencing, this, we have to find that circumference because that's the amount of fencing that it takes. The diameter there is 26 feet, 20 feet here, plus 3 feet there, plus another 3 feet on the other side. So it's 26 feet for the diameter all the way around. Diameter of the circular fencing that'll be on the outside. That distance is 26 feet. So the corresponding radius is half of that, is 13 feet, will work in terms of radii. So the area of the deck was just like what we just did. We'll take an outer shape, this time it's a circle of radius 13, we'll find that area, and then we'll subtract off the area of the inner circle, a circle of radius 10. So we'd have pi r sub fencing squared minus pi r sub p, radius of the pool squared. The radius of the fencing was 13, r sub f equals 13, with the letters I introduced. The radius of the pool is 10. So we'll subtract off pi times 10 squared. So that's pi 13 squared minus pi 10 squared, keeping up with the units. They'll be square feet, as area should be. 13 squared is 169, 10 squared is 100. That leaves us with 69 times pi. So we get 69 pi square feet, and that's the area of the decking. Very similar to the previous problem. Notice I'm always putting answers in little boxes. I put a box around the answer. I'll make tests out that are similar to that. I'll ask you a question and leave a little box, and you'll put your answer in the box provided. It makes you choose a particular thing for kind of a final answer. That takes care of the first part of the question. Second part was how much fence is required to enclose the deck. So that'd be the circumference of this circle. This outer circle has a radius of the fencing of 10 and 3 of 13. Right, we already did that. So we're looking for the circumference of a circle of radius 13 feet. We got a formula for that. The circumference of a circle is 2 pi radius. In this case, the radius of the fencing. So that's 2 pi times 13 feet, 26 pi. That's how much fencing is needed. You want to approximate this? No. Why approximate it? We got the precise answer. An approximation won't be the precise answer. You're taking a physics class or possibly a chemistry class. They want approximations, give them approximations. It's just an added step. You'd still have to do all this work. Now you want an approximation. You got to get the calculator out and make sure you use it right and enter the numbers correctly and get a numerical approximation of this. In math, it's easier. We'll just deal with exact answers and not worry about approximations and significant digits and those kinds of things. There's the amount of fencing. Back to the notes. And an idea of congruent and similar triangles is the last topic. Two triangles are congruent if each pair of corresponding angles have the same measure and each pair of corresponding sides are of the same length. In high school geometry, you establish some conditions under which triangles are congruent. I'd crudely say two triangles are congruent if they're the same size and the same shape. More of that soon. But in high school geometry, you're likely to show two triangles are congruent if two of the angles are equal and the lengths of the corresponding sides between two angles are equal. In other words, angle, side, angle. That's sufficient, ASA, sufficient to draw the conclusion that the two triangles are congruent. Two angles are the same in an included side. Side, side, side. Two triangles are congruent if the lengths of the corresponding sides of the triangles are equal. So, gee, that implies the angles must be equal as well because it's implying congruence. So if we have all this information about sides, we can draw some information about congruence. Side, angle, side, SAS. Two triangles are congruent if the lengths of two corresponding sides are equal and the angles between the two sides are the same. I won't bore you with the details of that. You dealt with this extensively in high school. Algebra will use these largely in passing. Two triangles are similar if the corresponding angles are equal and the lengths of the corresponding sides are proportional. All right, so informally, two triangles are similar if they have the same shape, but maybe different sizes, this idea of shape and size. Two equilateral triangles are similar, but they might be different sizes. You might have a little equilateral triangle and a big equilateral triangle. Well, they both got the same size because they're both equilateral triangles, but one might be bigger than the other. One might be have sides twice the size of the other, and that constant of proportionality would then be 2 to 1, for example. High school geometry, you have ways of determining if two triangles are similar. Angle, angle, if two angles are similar, if two triangles are similar, if two of the corresponding angles are equal. Yeah, but the angles of a triangle add to 180 degrees. So if two of the angles are equal, then actually all three of the angles must be equal. You might think of this as angle, angle, angle. It's stated maybe differently from what you encountered in high school. But if two of the angles are equal, then the third angles must be equal as well. So the triangles have the same angles and they have the same shape. But they might be different sizes because we didn't say anything about lengths of sides. Side, side, side. All right, so here we're talking about sides being in proportions. Two triangles are similar if the lengths of all three sides of each triangle are proportional with the same constant of proportionality. For example, we dealt with a triangle a while ago, had sides of lengths, I think it was 4, 5, and 7. We showed it's not a right triangle. Well, you might have a triangle with sides of length 8, 10, and 14. That's 2 times 4, 2 times 5, and 2 times 7. Okay, that second triangle, each of the sides are twice as big as the sides of the first triangle. Then those two triangles are similar by side, side, side. That's how that proportional idea is dealt with. Side angle side, SAS, dealing with similar triangles here. There's a similar side angle side dealing with congruent triangles, but it says two triangles are similar if two corresponding sides are proportional and the angles between them are equal. So we're not saying here that we have equality of the sides. We're saying we have proportionality of the sides. Upstairs, we also had a side angle side case, but here you're saying the lengths are equal. Whereas for similar triangles, we're saying the lengths are corresponding sides are proportional in length. So proportional becomes a story down here for similar triangles. Let's illustrate that a little bit more with a couple of examples, and that'll take care of this section. Here you're given two triangles, and you're told they're similar, and you're asked to find stuff. Find the missing length, x, there it is right there, and the missing angles A, B, and C. A, B, and C. So this triangle and this triangle are similar, you're told. That means they have the same shape, and that looks reasonable. Their sides must be in proportion, if that's actually the case. And it looks like this one on the right is, I don't know, about half the size of this one on the left in terms of linear distances. It looks like this is about half of that, but I'm not sure about that. Just eyeballing it, that looks reasonable. Let's do the mathematics. The angles are easy. Similar triangles have equal angles and proportional sides. So angle A corresponds to this 30-degree angle, so A must be 30 degrees. Angle B corresponds to 75 degrees, so angle B must be 75. Angle C corresponds to also to 75 degrees, so angle C must also be 75 degrees. These two angles are equal. This is an isosceles triangle. So that takes care of the angles. That's easy enough. We're looking for x. Notice you're given the side corresponding to x, given a 16 here, given a 12 on this side, and a 6 over here. So we've got this pair of corresponding edges and this pair of corresponding edges. We need to deal with a proportional idea. So we'll set up either set up a proportion or a ratio and say 12 is to 6 as 16 is to x, or something like that. In similar triangles, the lengths of corresponding sides are proportional. The side of length 12 on the left corresponds to the side of length 6 on the right. Those are the corresponding sides. So the proportion of the lengths of the sides of the triangle on the left to the triangle on the right is 12 to 6, or if you like, 2 to 1. Really is 2 to 1. This side is twice the length of this side. So yeah, the constant of proportionality is 2. This really is twice as big as this, or this is half as big as that. So the side of length 6 in the triangle on, 16, the side of length 16 in the triangle on the left corresponds to the side of length x on the right. That ratio of 2 to 1 tells us this must be half of that. So x itself must be 8 units. They didn't tell us what the units are. So there it is described in terms of proportions. We could also set it up in terms of ratios and deal with quotients. 12 is to 6 as 16 is to x. 12 divided by 6 equals 16 divided by x. Play with the manipulations, you'll also get 8 out. Dealing with ratios instead of dealing with proportions in this sense. It was defined in terms of proportions. I wrote it up in terms of proportions. Ratios might be a little easier to deal with though. And another one quite similar. These two triangles are similar. You're told find the ABC and the x. And this is it's almost identical to the previous example. Conceptually, they're the same. The numbers are different. The shapes of the triangles are different, but the concept is the same. Okay, corresponding angles will have to be equal. A equals 50 degrees, B equals 125 degrees, and C equals 5 degrees. Angles are easy. They gave us all the angles. You know, they could have given us only 2 of the angles and we could have figured out the third one, knowing the angles sum to 180 degrees. Now about side X, we'll do the proportions thing again. We'll say 10 is to 8 as 50 is to X. I've written it up to deal with it in terms of proportions. You want to deal with it in terms of ratios. You go right ahead, you'll get the same answer. So same story as before. The side of length 10 in the triangle on the left corresponds to the side of length 8 in the triangle on the right. This 10 corresponds to that 8, giving us a ratio left to right, lengths of sides, is 10 to 8, or 10 divided by 8 if you like, which we can simplify as 5 to 4. Divide 2 out of each of those, and it's the same proportion, it's the same ratio. So we'll take that ratio of 5 to 4 and say 50 is to X as 5 is to 4. Well, that's convenient. 5 times 10 is 50. So 10 times 4 must be X, and X must be 40. Same ratio. 50 to 40 is the same as a ratio of 5 to 4. Left to right is a ratio of 5 to 4 in terms of the lengths. You want to work it in terms of ratios and fractions. Go right ahead, you'll get the exact same answer. So it's the exact same concept, just a different notation. And that takes care of, our geometry essentials. So we'll move on to section 8.3. I think the topic there is polynomials, and we'll get into more algebraic things in that section. Have a nice day. I'll see you there soon.